Hello, in this video I'd like to go over the calculator permitted portion of our upcoming test number 2, which will happen on the 16th. I've got 3 practice problems here that I'd like to talk about and show you how I would complete them on the test. Let's get right into it. Number 1, the concentration of a drug in a person's body is modeled by this equation with C that concentration measures in milligrams per milliliter, and T is measured in minutes. And so in our derivative packet you probably saw this notation, C equals f of t, which equals the remaining function. What we're really trying to emphasize here is that in this particular case the concentration of the drug in a person's body is the result of a function that's based on time. And I share this notation with you because some textbooks and other courses tend to do this. But in reality, we could have omitted this notation altogether and simply said concentration is based on T. And that's fairly common as well. So I left that in there since I did take this from a textbook that used that notation, and it's worth seeing again. Now, you don't have to be a professional at understanding how medicines are metabolized in the body. I think with your understanding of calculus, you should be able to read and interpret this graph and hopefully provide some meaningful results. So let's do this first. Let's use our calculator to graph this and see if we can get an image of what's happening. So I've got the TI Inspire running. I'm on the home page, so I'll choose number 1 to create a new document, and I'm just going to add a graphs page right off the bat, number 2. Since the Inspire operates with x as the independent variable, I have to change the letter t to x. So we're going to enter the equation 20x times e to the power of negative 0.04x. Not a whole lot is visible right here, so I'm going to have to change the window. I don't really know for sure what window will work, but here's my thought. If somebody takes a drug or a medicine like this, I'm thinking a 24-hour time period would be pretty good to see the behavior of how the concentration of that medicine affects that person. So I'm going to graph from -3 to 24. I tend to, if I think 24 is going to be my upper limit, I make my lower limit about 10% or so less than 0. So 10% of 24, of course, is 2.4. Just use a whole number here, -3. This will give me a good view of the axes in the scale. And I'm not going to worry about the y-axis, and you'll see why in just a second. So I'll press OK here. There's my horizontal scale that I was after. Now I'm going to let the calculator figure out what the y-axis should be. So if I choose this zoom option and drop down to zoom fit, the calculator will fit the y-axis based on the x-axis that I've just selected. And there's that curve. So evidently a 24-hour time period isn't quite enough for this medicine to be metabolized, but it does look like we're reaching a peak. So let's jump in here one more time and adjust the zoom. We'll change our window settings from -3 to 24 to let's say 48. So that'll be -5 to 48. And of course this doesn't make sense because our time was measured in minutes, not hours. So we're not talking 48 hours. We're talking about 48 minutes. So shame on me for not paying attention to my instructions. Let's run this out to maybe 5 or 6 hours, which would be about 350 or 360 minutes. All right, one more time. Hopefully we'll get it here. So we'll go -40 to, let's just make it 400 minutes. There we go. Again, this 10% number is just something that I try to abide by, and this is what allows me to see the y-axis. If we chose 0 here, the y-axis would be right on the edge of our window, and we may miss some important behavior of the graph. There we go. All right, so now that's a little bit more meaningful to me. We see that the concentration rises to a peak and then becomes metabolized in the body until it essentially gets evacuated from the body and then levels off at 0. Now here again, I'm not a medical expert, but this is what I've inferred from the graph. We know our horizontal axis is time, so as time increases and our y-axis is concentration, we can see what happens to that concentration. The concentration increases to a point and then it decreases, and I'm inferring that it's the body that's metabolizing this, or it's being worn out or worn off, or its effects are being worn off as time passes. So let's go to the test here. Question number 1 for this particular problem asks if f prime is positive or negative, and is f prime at 45 positive or negative. So f prime at 15 and f prime at 45. Well, it's worthwhile to go ahead and calculate our derivative, so let's do that. F prime of t. Now this to me looks like it's a product rule because we have two functions that are multiplying together. Had this been just 20 times e to this power, then we could just use the derivative rule from our list, but this is definitely 20t times e to the 0.04t power. Let's use the product rule. The product rule says the derivative of the first function times the second function untouched, plus the first function, 20t, times the derivative of the second function. Now this is the derivative rule for e to the k x power. There's a multiplier times the exponent. And that said that we would bring down the k value, negative 0.04, and retain that same power in the derivative. And I'll let you decide whether it'd be worth your time to simplify this or not. It doesn't look too bad to me, so I'll simplify just a little bit. This first term we'll call 20e to the negative 0.04 t power. For this one, I'll multiply 20 times 0.04. I know that 20 times 4 is 80, and then if we have to move the decimal 2 places to the left, I'll call that 0.08. Sorry, just 0.8. And we have this negative sign, so we're going to subtract 0.8 t times e to the negative 0.04 t power. And it might be worth noting that we've got a common factor, e to the negative 0.04 t power. So if we wanted to take this just one step further, 0.04 t times 20 minus 0.8 t, this could be a pretty good description of our derivative function. Now that's important to note because we're being asked about f prime at 15 and f prime at 45. Since the calculator is available, I'll just execute this function at the number 15 and the number 45. So I'll press Control Dock and add a calculator page now. And actually, let me share with you a little bit of a trick or a benefit to using these calculators. I'm jumping back to the graphs page. I'm going to press Tab again to activate my function bar. And I'm going to write that new function that I established for the derivative here. E to the negative 0.04 x, drop down, parentheses, 20 minus 0.8 x. Now that graph doesn't, or may not mean a whole lot to you right now, but the reason why that's going to be helpful is when I switch back to the calculator page. If I want to execute that function at a particular value, then when I press, try that again. When I press this variable key, the function 1 and function 2 pop up on the screen. Those are the same function 1 and function 2s that we had stored over here. So f2, the red function, is what we established as our derivative function. So on this calculator page, if I say execute f2 at the number 15, well, now I've got the value for the derivative at 15. And so I don't need to show a whole lot of work here on the test because I know you're using a calculator here. And we've got 4.0 4.3904. Now, let's talk about units, though, real quick. The unit is, again, the combination of our horizontal and vertical axis. So our horizontal axis was milligrams per milliliter concentration. Sorry, that was our vertical axis, milligram per milliliter, and our horizontal axis was time in minutes. So at F prime of 15, which is positive, we are increasing at a rate of 4.39 milligrams per milliliter per minute. That's how fast our concentration is increasing, because F prime of 15 is positive. We know that it is increasing. Now we can do the same thing. We can call the variable F2 again and evaluate it at 45, and we get negative 2.6447, 48 when rounded. And again, this is milligrams per milliliter concentration per minute. And so that's a negative result, and that means that our concentration is decreasing, or the drug is wearing off at that time. And so with that knowledge, or with that interpretation, we can now provide some sort of written statement in Part B. And your description doesn't need to be very elaborate. This would be sufficient. The concentration of the drug is increasing at 15 minutes and is decreasing by 45 minutes, or at 45 minutes. And if you wanted to add a comment saying that, well, when the slope is negative and the concentration is decreasing, that the medicine or the drug is wearing off, you might add something like that. And that would be just fine. For question 2, the distance traveled in feet is a function of time, t, in seconds. So we've got feet and seconds, y-axis, x-axis, vertical axis, horizontal axis. When we answer these questions, we are to include appropriate units. So f, f of 10, the function evaluated at 10, that's pretty straightforward, would be equal to the square root of 10 cubed plus 1. So on our calculator page, you know what, I'll probably go to the home screen and just create a new document, and I won't bother saving this one because we're done with the last example. But on the calculator page, we'll take the square root of 10 cubed plus 1. We've got 31.6386. 31.6386. And since this is the function, not the derivative function, we know that the unit should be feet. This function is the same as our distance calculation, and distance, we were told, was measured in feet. So after 10 seconds, this object has moved 31.6386 feet. Now f prime of 10, well, we need our derivative rule here. So let's go back to this function and calculate the derivative. Rather than relying on the derivative rule for this radical, I'll remind you that sometimes it's beneficial to think of this as a fractional or rational power. So we've got t cubed plus 1 to the 1/2 power. That's the same thing as the square root. And now when we evaluate the derivative, we can use our power rule along with the chain rule. So we've got 1/2 times t cubed plus 1 to the negative 1/2 power after we reduce by a power of 1. We have to immediately multiply that by the derivative of the inside function to account for the chain rule. And this 1/2 multiplies by this expression, but this expression is also being raised to a negative 1/2 power. So that gets moved to the bottom. We've got 1 over 2 with t cubed plus 1 to the 1/2 power. Now it's a positive exponent since I've moved it to the bottom of a fraction. And the 3t squared, well, that's kind of like a number over 1, so the 3t squared gets listed in the numerator. 1 times 3t squared is just 3t squared, and in the denominator, I'll go ahead and rewrite this as a radical again. The 1/2 power is the same as a square root. And I'm doing that so that it mimics the original equation more closely. The layout of our derivative is more similar to the layout of the original problem. So we now have the derivative rule. We can evaluate the derivative of the function at 10. That would simply be 3 times 10 squared divided by 2 times the square root of 10 cubed plus 1. This time I'm not going to bother putting the function into a graphs page to evaluate it. There's no real need for that since there aren't any additional problems associated with that function. So I've created a fraction, and in the numerator I need 3 times 10 squared, and in the denominator I need 2 times the square root of 10 cubed plus 1. And this result comes out to be 4.71 or 7410. 4.7410. Now that we're talking about a derivative, we're talking about a combination of the distance axis and the time axis. And our distance was measured in feet, our time was measured in seconds. So the unit of our derivative is 4.74 feet per second. So with just a little bit of math, we recognize that this object that's moving after 10 seconds has moved 31.6 feet, and at 10 seconds precisely is moving at 4.74 feet per second. And all of that was obtained by one function and the derivatives that were computed from that function. And for the last example in this video. This problem should look familiar since it showed up in your derivative packet. The number of acres of harvested land in a region is given by this function, and T is the number of years since farming began, and N is the number of acres. So we know our vertical and horizontal units. So we've got number of acres and time. We can evaluate this function at 9. That's simply 120 times the square root of 9, which equals 120 times 3, which is 360. And we're talking about the original function, and the original function, which is the same as n, tells us 360 acres are being harvested. So 9 years after farming began in this area, there are 360 acres that are being harvested for farming. F prime of 9, well, let's slide this out of the way and find our derivative. Well, the derivative, we've got a constant multiplier, 120, and we're multiplying that by the derivative of the square root of t. And I know from my derivative rules that the derivative of the square root of t, or x, would be 1 over 2 times the square root of t. And we can combine this, 120 over 2 square root t. And now that simplifies to 60 over square root t. When we evaluate f prime at 9, we need 60 divided by the square root of 9, which would be 60 divided by 3, which is 20. Now that we're talking about a derivative, however, our unit has to be a rate. And again, back to this idea where we had the number of acres per year. So we had number of acres along our vertical axis and time in years. We know that the rate at which the amount of harvested acres is increasing is 20 acres per year. So again, after 9 years after farming began, there are 360 acres that are being farmed this year, and that was an increase of 20 acres per year over last year. When we calculate part C, we're being asked to find f prime of 9 divided by f of 9. And this calculation is sometimes called relative change or percent change. And it's pretty helpful for us to investigate what's happening in a real-world situation. So rather than including the units, since I know that this is going to be a relative change or a percent change, I'm going to recognize that we're going to report our answer as a percentage here. Now 20 divided by 360, 20 divided by 360, I'm going to press Control Enter to get the decimal, is 0.055 repeating. And if we were to record that or report that as a percentage, this would be 5.55% growth. So perhaps you can imagine that if a region begins farming, then the growth is pretty quick at the beginning, but evidently 9 years into this experiment, or whatever you want to call it, 9 years in, the growth was 5% over the prior year. And so we could say that there was a 5.5% growth rate at year 9. And this would be different than the growth rate at year 1 or 2 or 10 or 1,000. And you can investigate that on your own if you'd like. So as far as the test 2 calculator permitted portion goes, we're just going to have 2 questions on the calc permitted. And the 2 questions are going to have multiple parts, kind of like what we have seen in these last 2 examples. And I will ask you to complete both. So I hope these last 2 videos help you understanding the preparation that goes into this test. Ideally, the derivative packets would suffice, but now you've seen at least an example of some of the types of questions that you'll see on the test, and you may have even noticed that some of the problems showed up in our derivative packets. The only work that was not in our derivative packet that will show up on the test is implicit differentiation, but you've now spent a fair amount of time with that and practiced with it on Math Excel. So I certainly hope that you'll be prepared. If you've got further questions, please let me know. Thanks for watching.